So what we will do next is to, give you some slides, a short presentation about how MCS functions, and then we are going to run it using a separate setting that is next to me here, and then also look at some of the input and also look at the output. So I think this is everything here has been said already. Like you see there, the phases that are modeled are melts, and solids that are considered by the melts algorithms, and then possible H2O plus minus CO2 fluid, if that is relevant to the system or is stabilized. Resident magma and wall rock and then recharge pulses are the subsystems in magma chamber simulator. And again, the sketch, what is being modeled here, we have magma crystallizing, accumulating, recharged magmas coming in, energy going to the wall rock, mass coming out from the wall rock. Something that it would be good to mention here is that you can model assimilation two ways in MCS. Another one is the heating, like you just heat the wall rock, it starts partially melting and the melt is then being assimilated. But you can also do this kind of bulk assimilation, like in De Paulo's AFC, a little bit like that. So just like put in blocks of solid wall rock, you fool MCS so that you actually put these stoped wall rock blocks as recharge magma. So you just shove them in the magma chamber, and then it does the same thing than in the recharge case. So it equilibrates during one step. It tries to find equilibrium with that stoped wall rock block when it's introduced into the magma. And sometimes result can, for example, be a crystallization of a new phase, or a lot of, like a high amount of crystallization, or maybe sometimes complete dissolution of the wall rock block, depending on the phase equilibrium. So some words about the computational environment. Visual Basic in Microsoft Excel, which is not the most reliable tool and not a good option for long-term evolution of MCS, or so that people could use this like 10 or 20 years from now. We've had a lot of issues with Microsoft Office updates, that a new update comes in, suddenly MCS doesn't work. Especially with Mac, we have had to deal with these issues, not so much with PC. But the reason that we are using Visual Basic is that the main programming team that already started, or the main programmer of the whole MCS team, Guy Brown, who is an old colleague and friend of Frank Spera and Wendy Borson, he was an expert on Visual Basic. And of course, when certain people come together, they use what they know best. And this is why we have developed this, or they have developed this in Visual Basic, and we are still continuing to do that. And of course, it's a tremendous job that Guy Brown has done in order for this to be even usable in Visual Basic. But in future, there are plans. We are actually looking for funding with the team to get this translated to some other programming language, maybe Python or something else. We'll see. Nothing yet concrete in that realm. So all modern PCs and Excel versions should work. Like I said, like I wrote in the email, there's a lot of troubleshooting documents on the website which you can use. And usually when people ask some questions from me that I didn't get this functioning or there's trouble, you can usually find that from the troubleshooting document. So a lot of the issues have been dealt with, and there are explanations how to go through with them. Within my realm of colleagues here in Finland who have used MCS on different settings, I think it has been functionable in if not in all of them, at least almost all of them, without much trouble. So if you just don't get if you don't lose your hope during the first try and try a little bit more and just read the troubleshooting, you should be okay with PCs. With Macs, we have this trouble with this Microsoft Office updates. So you can check the website for details for which Mac versions and which Microsoft Mac Office versions this program is compatible. But it's funny, we actually started with Mac because Melts was a Mac software as well. So we were first using Mac and we were having a lot of trouble with the updates. And then they made a huge job in Guy Brown and some of other Frank's and Wendy's colleagues made a huge work in translating this to PC, which I think is more stable in general. I am using Mac today in modeling, but I will show you what to do with the PC version as well. So flow chart of this second session, we will look at the input. We will run the software, an example simulation. We will look at the output and the box model visualization. I think we don't have to go too deep into that because you already saw in the first presentation what was going on. And this is for thermodynamics and phase equilibria and major element evolution. Then trace elements are modeled using a different software, which is of course part of the MCS, but is a different executable in the MCS folder. And MCS traces is naturally completely dependent on us having results from thermodynamics and phase equilibria. So this has to be always run first in order for MCS to determine the phase equilibria and major elements. Those have to be known in order to be able to do any trace element modeling and calculations. So always do this first if you want to model trace elements and isotopes. And we will look at that as well. Input, short overview on running the simulation, how we can upload and save partition coefficients in that interface, and also looking at some of the features of the output. Okay, so the simulation today is the one that we already talked about in the first presentation, taking place at 100 megapascals, 1 kilobar. We have magma, continental depleted basalt, wall rock, average upper crust. There's no stoping here, no, not fooling MCS with recharge of wall rock, but just this partial melt assimilation scenario taking place. And then 2 recharge events that have the same composition with the parental melt. Something that is related to the question that was given to me or asked during our break. The first recharge is hotter, as hot as the parental melt, so it's completely liquid, about 1100 degrees Celsius. But the second one is a little bit more cooled down, so there are already some crystals coming into the magma chamber in the second recharge, and this will have some effects that I discussed and that you will then see in the output. Okay, so now we are going through the input file, and maybe I will show this to you where you can find it, and you can either follow me because I will show all the parts here on the Excel file, or then just go through that file on your own. So in the online resources folder that I sent you, there's MCS input there. And the file that we are looking now is MES R2 AFC input, which is the input file for this scenario. So it looks like this. And I have basically taken screenshots of these different parts, and we will go through them in this presentation. So I'm not just scrolling through that. It's easier to show them here. So first part there is the system variables, which are kind of like the overarching variables for the system. Although first of them is for the wall rock, which is the FM0, meaning the wall rock percolation threshold. How much wall rock has to be molten before assimilation commences. So this is not actually calculated by any kind of code. This is a value that you select based on publications about the certain rock type that you model as your wall rock, in what is the percolation threshold, or what that would be in that kind of wall rock. Of course, it doesn't change that much in different silicate rocks, but if you have something else, like highly carbonaceous wall rock. If you want to try to model something like that, then it probably would be smaller than the 0.1 value that is the default value, meaning that the wall rock has to be 10% molten before any assimilation takes place. So this just kind of like tries to follow the natural process of assimilation in a way that not instantly when some melt forms in the wall rock, it gets assimilated, because of course there has to be enough melt in order for it to escape the wall rock. Excluded phases, you can, if you don't like a phase that you don't want to see in your system, you can try to exclude it. This is usually not recommended because, of course, MELTS is a thermodynamic tool and it tries to find the phases that are in equilibrium. But if there's something that just, you know, comes about, some weird phase for weird reason just comes stable in your system, you can exclude it here by just writing the name of it here. But generally not recommended. Maybe in some cases, or if you use it, you always, of course, have to acknowledge it, so saying that, okay, I did this model, but I excluded this and that phase. System pressure in bars. So here, the pressure is 1 kilobar. Enthalpy convergence steps, 30 steps. This is just a computational thing that I think you don't have to worry about. It's no matter in how many steps the MCS calculates enthalpy convergence between magma and wall rock. Nothing that you should change, but it's still changeable if you want to change it. You can also select oxygen fugacity. Here is none, meaning that we let the system define the oxygen fugacity. But you could write here FMQ or NNO or FMQ +1 or something like that. And then the system would be open for oxygen. So it would force the system to stay in that oxygen fugacity throughout the run. Usually modeling with none is probably more ideal, because in that way the oxygen fugacity of the system can change, and it's actually change because what happens in phase equilibrium, what crystallizes, what is being assimilated. The next rows after that are the initial magma composition. And as you can see here, I will say it now directly or in the beginning, because this is related to oxygen fugacity. So for this composition, that is the parental magma, we have calculated how much there's Fe3 plus and how much there's Fe2 plus. So if you would keep oxygen fugacity none, and you would only have Fe2O3 total or FeO total, then it would assume that all of that iron is of that species. So if you are using none here, you should have this predefined for your melt and for your wall rock. And after that, the oxygen fugacity will change according to phase equilibrium. Major element composition normalized that always to 108%. If you go right from here, you will find some cells that do normalization, so you can do the normalization easily in the worksheet itself. Start temperature. I usually put a very high number here for the starting temperature, because it always drops down to liquids. In MCS, it's not possible to model superheated liquids unless you do a little bit recharge tricks, but the modeling always starts from the liquidus of the parental melt. So even though that number is high, it will always drop to the liquidus in the beginning, unless, of course, you have a temperature that is lower than the liquidus. Then it will crystallize a lot of stuff already in the first step. Temperature decrement is the amount of temperature, or the temperature, well, I guess you can say the amount of temperature that, well, it's not amount, but the degree of temperature that drops every step in the model. And 5 degrees drop is kind of like a standard that we have used. You can use a higher or lower value for that. If you use a lower value, you will get more detail. If you use higher value, you will get more faster model and kind of like a system that is more similar to actually equilibrium crystallization. So within this 5 degree step, drop in temperature, the MCS calculates equilibrium. Like, what is the equilibrium consequence of that 5-degree drop in temperature? Some crystals probably form. In the end of that step, the crystals are removed. And then there's another 5-degree drop, equilibrium calculated, crystals are removed. So MCS is not a pure fractional crystallization model or pure equilibrium crystallization model. If you have high value for temperature decrement, let's say like 20 degrees, then there's a 20-degree drop within which everything happens in equilibrium. And only after that, in the end of that step, the solid mass is fractionated away from the system. If the temperature decrement is very small, then there's a lot of stuff moved away, or every 1 degree decrement, there is solid material removed from the system, which is more closer to ideal fractional crystallization. And this is actually quite useful. It may give some hints in how your system was behaving if you compare results using different temperature decrements. Then after that, you can decide when the model stops. You can give a hard stop melt mass in magma, how much melt left in the chamber, and then the model just quits. Or hard stop temperature, meaning that when the system cools to this temperature, then it stops and it's ready. These are very useful if you are just interested, let's say, in very early phases of what is happening in your modeled system. You don't want to always run it all the way to the final equilibrium. You probably want to save some time. So you can give a temperature, for example, like 1000 degrees, and you are not interested in what happens after that. So every model stops when it gets down to 1000 degrees Celsius, for example. Very useful cell if you want to save some time. Okay, below that is the wall rock composition then, and exactly same thing. You can see here in this default run that we are running, oxidation state of the iron has been predefined. And something that you see here and also in the magma, that you don't have to input all the oxides. So for example, nickel and chromium and cobalt oxides here are 0. Their concentrations in this magma are so small that they are considered as not important. And also same here for the wall rock. So you don't have to input all the oxides. But of course, if you don't input oxide, that doesn't take part in the phase equilibria calculations then. So you just have to acknowledge that. Something related to the volatile species question earlier, you can see that already in MELT's input sheet and in this MCS input sheet, we have a place for sulfur, chlorine, and fluorine, but they are not yet available, unfortunately. The computations are not complete, maybe someday. But I know these have been here in the MELT's interface for a very long time. So maybe it will still take some time. Okay, so then there are the temperature constraints for the wall rock. There are some of these are values that are not very easy to actually explain here. It's more easy explaining them when the model is running. But something that is quite straightforward is the initial wall rock solid mass, and it's given here as grams, although it can be any units. It's 200. And it always compares to 100 of the magma. So the parental magma is always 100 units. It can be grams or whatever. And here the wall rock is 2 times that. So 2 times the mass of the magma is the mass of the wall rock that will take part in this simulation. Another one that is quite easy to explain is the wall rock initial temperature. So the initial temperature of the wall rock is 700 degrees. It means that this is in some very active rift environment. It has already been preheated quite a lot by previous magma pulses. Of course, the more cooler or colder your wall rock is in the beginning, the more crystallization and energy it will require from the magma in order to heat it enough for it to melt. Okay, these other values are then related to us finding or kind of like constraining the melting behavior of the wall rock for melts and for the simulation. So It's called the find solidus procedure or Walrock priming procedure in MCS. As I said, don't worry if this doesn't sound understandable now. It will make more sense when we look at the model itself. Anyway, we define a start temperature for this find solidus procedure and end temperature for the find solidus procedure, and there's also a temperature decrement here. So in order to kind of like I think the best way that I found out or how I found out to explain this so that it makes sense is that we want to know what happens in Walrock very close to solidus. So when the first drop of melt forms, and in order to do that, it's not easy for melts to approach this situation down temperature, so from cool temperature, because MCS or melts, it doesn't understand phase equilibria in low temperatures. If there's no melt present, melts usually cannot give you a phase equilibria. It doesn't calculate phase equilibria for solid rocks. So in order for us to know the composition of that first drop of melt, we have to approach that melt from high temperature. So we start with temperature here 880 degrees, and in 5-degree decrements we drop down to 700 degrees. So we go from high temperature to low temperature, so that there's first a lot of melt in the Walrock, and the amount of melt diminishes, decreases until we reach that first initial drop of that Walrock at as low temperature as possible. So we are trying to find that composition in that first drop of melt, and we have to approach it from up temperature in this priming operation and not down temperature. So ideally, the starting temperature would be so that the Walrock is around 40 to 60% molten, so about half molten, and the end temperature would be just below solidus. So this may require some testing. If you start with a new Walrock composition in MCS modeling, you may have to try a couple of times in order to find what is the good temperature for the starting temperature and for the ending temperature, so that you can actually prime the Walrock behavior. I hope this makes sense how I said it, but we'll see when we are running what it actually does. Then the recharge events, and now I'm showing the recharge event number 1, the same composition than with the parental melt. In the latest version of MCS, there are up to 30 recharge events possible, so you can just push in new magmas in quite many times. And it's, I think in one of the publications that we did, we used 25 recharge pulses in one of the studies in about Samoa volcanic system. I actually wasn't involved in that myself, but one of the publications from MCS team. So a lot of recharges that you can input in. Again, same thing, major element composition normalized, iron oxidation state predefined, mass, again, relative to 100 mass units of the parental magma. So this is 75% of that mass, 75 units. Recharge magma temperature. So what is the temperature of the magma when it comes in as a recharge? Then the recharge trigger. And there are 2 ways of defining what triggers the recharge. Either when the temperature drops in the magma chamber to this value, then the new recharge comes in. Or after the magma has dropped a certain amount of temperature. So, for example, this second option, where you define how much the temperature of the magma has to drop from previous event to add another recharge, may be useful if you have a lot of recharge events. So not just trying to understand, okay, I put it in this temperature, well, what will be the temperature after 20 steps? I don't know. So sometimes it's maybe easier to define that, okay, the temperature drops this amount, and then we will have second recharge event. Then let's say 30-degree drop in the temperature, then the third recharge event, and so forth, so forth. So different ways of defining when the recharge occurs. And which of these options is used is actually defined just above this line here. So So here in this cell, B63. So here it's defined by the temperature and not the delta temperature value. Okay, I guess that's it. So let's go to the simulation itself. So I will now stop sharing this screen, and I will show you, well, I don't stop sharing. Let's continue sharing, sorry about that. I will exit this presentation for a while. And I should show you, now I'm in a PC environment. So this is the PC version of MCS. You should have it installed in Documents and in MCS folder. And if you have installed it properly, it has created these different folders and these different files inside of it. So what we are using now is the MCS phase equilibrium PC executable here. And if you now, before you do that or open that, you should not have any other Excel files open. So close Excel completely. Only this file should be open when we run the simulation. So that should open in Excel. It asks a couple of questions. Enable the functions, I think, and another one, and you have to find the MCS path, but those are very easy and straightforward. I won't start them here because I'm running the Mac version, but just to let you know that this is the program that we are running now. Something other that is specific to PC environment is the command prompt. I have it here pinned in my taskbar, but if you don't have it here, you can find it. Of course, this is an old version of Windows, as you can see as well. But you can search it from your program list by just typing command prompt, and it should be found there. There you go. And for this run, because we are running recharge, assimilation, fractional crystallization, we need 3 different melts engines. So melts engine running the Magma, melts engine running the Wallrock, and melts engine running the recharge equilibrium. So you would need to start 3 of these. You can always go back here, but once this is open, it should now be available here in the taskbar. So you can open another one here by clicking the middle button in my mouse. If you don't find it, you can always go and try to open it 2 more times from here. So you need 3 of these command prompt windows open on your PC setting, and then just start this. And then now I will switch to Mac, but basically when I'm doing this thing with Mac, I will explain how to do that in PC. There's not much difference in that. I think the biggest difference is that this is just called command prompt, and you may have to try to find it from there. And on Mac, it's called a terminal window. Otherwise, everything is the same. So I won't need these anymore. So you can already open it on your computer if you like. So now we are in our Mac, and as you can see, and I think Bill mentioned this when we were testing that this looks a little bit more up to date than my PC. Yes, this Mac setting that I'm using has been completely devoted to MCS, so I'm only running MCS simulations with this one. Okay, so on Mac setting, we will open the terminal. And you can either open 3 separate terminal windows, or what I like to do is that I open 3 separate tabs into that same terminal window. So PC users, your command prompts are already open. You don't have to do this. And with the command T, you can open new tabs into this terminal window. And again, we need 3 of those. So for Magma, for Wallrock, and for the recharge. Then I already have my documents folder open here. These are probably quite small, the fonts here. I don't know if I should zoom in, probably not at this point, but I will zoom in when we are using the software. So MCS folder in documents. Or should I zoom in here? Will, is anything visible? I don't know.
Yeah, I mean, I can just about make out the files there, and I can see the command prompts.
Yeah.
Yeah, perhaps just read out the file name you're clicking on as you read, just so people can hear, and I think you're good to go. Okay,
thanks. So, so this is now the MCS folder. There's input and output, Magma, MCS VBL code, recharge, Wallrock. In input and output, we store all the input files. So when you have downloaded and installed MCS, there already should be some files here. When I open this, as you can see now, there's like 200 files because I've run a few MCS models. But just showing that you can store all the input. All the input files start with this MES prefix, like the one that I already opened and showed you. So the one that we are using today is the MESR2 AFC input, which is the one that we already looked. So it should be in this folder. I think it is there. Okay, now I went a little bit too far. Let's close input and output. And the software itself, you can find it from the MCS VBL code folder. And again, I have several files here because I have different test versions of this. So I've used different versions of MCS. You should probably only have one of, I think, the AH version, or is it AM, which is the latest one. But anyway, you should only have one MCS phase EQ version here. Then you have the trace element engine that does the trace element calculations. There's one for recharge 30 for me, and also one for the older version. So I think you only should have one of these as well. And then the trace element isotope software executables. So we are doing the major element phase equilibrium run. We will open this version here. The only version that you have there, and the latest one that I have. Enable macros. Welcome. Okay. And then you have to always choose the MCS folder, so the Visual Basic knows that you are in the right folder. So you have to choose that one. If you are not in that folder, you have to, of course, search it from your documents folder, but it usually gives it as your predefined folder. So choose that one. Okay, now I think I will zoom in a little bit so you see all the texts. So these are the different steps that you go through when running MCS. Melt's terminal commands are the commands that you initiate Melt's code with. Then you can select the input file and create the name for the output file. Then we do the find Wallrock solidus procedure, the Wallrock priming procedure that I was trying to explain previously. If you use the same Wallrock for several different runs, you don't have to go through that phase every time. You can just use the same Wallrock thermodynamic behavior that you did in your previous run. This again saves some time if you are using the same Wallrock in your simulations. Then the main thing, running MCS. Also, if you just want to run fractional crystallization or recharge, you don't have to go through the Wallrock priming procedures. You can just directly start the run after going through steps 1 and 2. So that will save you some time. Then exports run results. There are some graphs that you will see when the simulation is taking place. You can align them if you like. Here are the names of the excluded phases. If you want to exclude the phases from in the MES input file, you can check them from there. But anyway, I've never excluded any phases, so I haven't really used that one. I've been happy with the phases that I've seen. Okay, so melts terminal commands. You can click that one. It opens a window. Now something to make sure with this run that we are running, select the correct melts version from this menu. And we are using the version 1.2.0 to highlight melts. Something that is a little bit confusing is the name Rhyolite melts, but it just means that in the traditional melts algorithm that was developed already in the 90s, some information about felsic systems have also been introduced. So Rhyolite melts also works for ultramafic systems and mafic systems as well as the old melts. It's just that felsic systems have been added to. But for people who don't know that background of the melts, saying, okay, I modeled picritic magmas with Rhyolite melts, it may sound a little bit weird, but don't worry about that. So you selected 1.2.0 Rhyolite melts, put in clipboard the Magma melts command. When you see these hashtags appear here, then it should be copied to the clipboard. And then you add it in one of these terminal tabs or on PC on one of your command prompts. And on PC, if you right click in a command prompt, you should be able to select paste there and press enter. So I will copy that and then I will paste it here. And then press enter. And it started running. If you see a message like this, you see these different rows and mentions about Rhyolite melts, then it should be running fine. So that's for the Magma, one for the wall rock. And then one for the recharge. So we have Magma running, we have wall rock running, and recharge running. I mean, the melts engine is prepared to simulate these subsystems. So that is now fine. Then we can close down the terminal window. No, not the terminal window. Sorry, that interface window in MCS. Terminal window should stay open here. So don't close it or don't close the command prompts. Sorry about the poor choice of words. Then we are ready to input the file name. You can, I will usually put a lot of A's here in the beginning when I'm running test runs, because I have so many output files that I want to find it as the first one in the pile, but you can use any name that you like. I think it should have at least 6 characters, so maybe you can write anything there. I will just write AAA test or something like that. And then we select the correct input file. These are probably quite small again, but again, you shouldn't have too many of these unless you have run MCS for many weeks already. So we select the MESR2AFC input, which is the input file that we just went through. And then finish. Okay, so here we are. The next step is to find the wall rock solidus. Wall rock is involved in our simulation. We now want to define the composition of the final melt drop in the system. So let's click that. So now you see that it started from a temperature around 900 degrees. So I think in the input file, it was 880 degrees Celsius. And you can see that about 60% of the wall rock is molten. So this is a good value for that input. And now we are going down temperature in 5 degree steps, in kind of like trying to find the last drop of melt in the wall rock. So you can read the wall rock temperature dropping here, and you can read how much melt there's in the wall rock. And you can see it's steepening there, the trend, meaning that some phase the phase equilibria define that there's actually not that much melt present at those temperatures anymore. So you can see that it's not a straight line or a curve, but it reacts to phase equilibria changes in the wall rock. So then it should end with a message like this wall rock is primed at temperature 740 degrees. The wall rock there is about 8.9% liquid. And this temperature that it's selected is based on the FM0 value of the input. So at this point, it's about 10% molten. And the temperature then, when it's about 10% molten and assimilation is about to begin, temperature is then 740 degrees Celsius. So we are ready. We found the last compositions of the melt here. We found the composition of the melt when assimilation starts at 10 weight%. So now we can actually start heating this wall rock from down temperature when we know how it behaves. So if everything is fine, we can just run MCS. So you can see magma temperature starting to drop, the amount of liquid in the magma starting to drop, meaning that something is crystallizing. You see that the wall rock is soft coupled, meaning that it's already a little bit molten, but not yet ready to be assimilated. So not yet 10% molten. Now the wall rock temperature is 740 degrees, meaning that it's 10% molten. And now we start to see assimilation because wall rock is heated enough. So there's more than 10% of melt in the wall rock, and it's now being assimilated in the magma. And you can see the temperature of the wall rock continues to rise. What doesn't rise is the amount of melt in the wall rock. It stays always around that 10% because every drop of melt that forms above that 10% threshold gets assimilated in the magma. Because the percolation threshold of the wall rock is 10%, everything above that 10% gets assimilated. And you can now see in your command prompts or in your terminal windows the melts functions running, and it's calculating phase equilibria every step. So now something crazy happened. You can see from the major element diagrams, the trend suddenly pulled back to the initial composition. Of course, that marks the first recharge event that was written in the input file. So if you see something like nothing happening on your Mac or on your PC, make sure that this window is active. Otherwise, the calculations are not working. So I think what I will do now is that you can keep your model running and I will keep it running on this Mac, but I will now switch back to my PC here and continue with the presentation, because there's no point of me just waiting for the model to run. This is quite a complicated model because we have assimilation and recharges taking place. So this should take about maybe 5 or 10 minutes. That's usually the amount of time that goes into these kind of more complex models. And of course, if you are running only fractional crystallization, those are faster. We are working on a Monte Carlo application of MCS, where you could just put a set of input values and maybe variation ranges, and you could just start MCS and it would run overnight, and you would, in the morning, you would collect all the output and just select the best fit results. But currently we have to run every run manually. So that's also one good reason to have a separate modeling computer if you want to work on something else. But I will stop sharing here. Or am I very close to equilibration? No, it will take some time yet. So you can still see that the magma temperature is about 150 degrees away from the wall rock temperature. So magma temperature still dropping, wall rock temperature climbing. So stop sharing. You can keep yours running. And I will return to the computer here. So when your model stops, when everything is done, MCS will give you a notification that the model is complete, equilibrium has been found. Then the only thing you have to do is to export the run results. And you will then find that file based on the name that you gave to it or predefined to it. You will find it in the input and output folder. And how it looks like is basically like this. We haven't done any of the trace element calculations yet, so only thing you see are the first tab that you should see at that point is the input tab. So every output also stores the input from the MCS run, which is of course useful. Then you don't have to keep track on your own that, okay, I use this input file to produce this output, but you always know that, okay, this was the input that I used to produce this output. And the most important tab is the run summary, where you can read a whole lot of variables that change during the run. We will go through them step by step, but just you can see that there's quite a lot of information stored here from different compositions and different thermodynamic variables, and then also masses of the different phases. After that, there are different kind of diagrams that have been pre-defined by or predefined by MCS. So you can, for example, follow your run in TAS diagram. There are mass fractions of the different phases stored as a diagram, phase proportion percent, phase masses, and so forth. And you even find the solid formulas for the, and I think in the most recent version, you also find the major element compositions of the different solid phases. So you can also follow the composition of the mineral that crystallized at a given step. First, there are the wall rock phases that were recorded during the priming operation, and then the run phases that were stable in the run at a given temperature are then stored here in the beginning. So first it was olivine, then kind of pyroxene and olivine and so forth. Okay, so actually my Mac now says that the model is ready. You can press OK and then export the results, and you will get the output file stored, but the output file has already been given you beforehand, so you can also check on that one, which way you wish to do it. So again, I'm doing the same thing than with the input. I think we have to go slightly fast through it, so we will have time here. but you can see the screenshots from the output Excel file here on the left side of my slides. So melts run mode, magma chamber process, it tells you whether fractionation is happening, whether AFC is happening, whether recharge is happening. It records magma temperature, wall rock temperature in the following cells. Magma cools down, recharge heats it, recharge, second recharge even heats it again, and the wall rock is warming up until they find the final equilibrium in the run. Mass of crystals, how much there's melt in the system, how much there's crystals every step, and how much there's total crystals is recorded. And as you can see, when the recharge comes in, the amount of melt always increases. However, if you remember, the second recharge was a little bit cooler than the first recharge. So in the second recharge, there were some crystals already present, which you can see here that when the second recharge comes into the system, we have actually a lot of crystals crystallizing during that one incremental step. And you can see the increase in the cumulative amount of crystals in the magma chamber as well. So it records the consequences of more cooler magmas coming in, although not recording any xenocrysts, but kind of like recording the thermal equilibrium of these two different magmas. Something that is important to point out, the R value, like in the De Paulo's AFC equation, the mass of assimilation relative to mass of crystallization is not constant. So it varies depending on the phase equilibrium. As you can see, the R value changes from, well, this is not the R value, but this is the amount of incremental assimilation. It goes from to 2, about 4 to about 10. Then it decreases again because there are the recharged magmas and the phase equilibrium changes in the wall rock influence how much melt is being assimilated every step. So R value is not constant, very important to point that out. Different phases recorded here. Clinopyroxene is the most common phase. Plagioclase also important. Orthopyroxene appears here in about after simulation step 40. Then there's small amount of fluid and small amount of ilmenite crystallizing. So all this is readable and acquirable from the output file. Wall rock becomes more mafic. It almost starts to be like some kind of anorthosite. Potassium feldspar, KFS, it starts decreasing. Also quartz starts decreasing. These are the phases that preferentially go to the melt, contribute to the melt phase. So of course, naturally, the wall rock gets more and more mafic when the simulation proceeds. Okay, then a lot of things happening in these major element diagrams. They're a little bit more different than just these binary mixing or straight model lines that you usually see. I think we don't have to go in detail through them. These materials will be distributed, so you can then follow what is happening in detail in them. I'm trying to, for example, find out what is happening in a certain point when you compare it to the output. And we went through the mineral composition output as well. And also the visualizer. You can always look at this output that was produced in the visualizer software. Okay, that's it. I think we will now move back to the Mac modeling environment when we will run the trace element simulation on top of this. So I will stop sharing here. Or let's see, actually, I think, yeah, not yet. Let's look at a couple of things here. So now we have the phase equilibria and major element models run. We can now also run trace elements. And in MCS, it's possible to model 48 trace elements and 8 isotopic system, including oxygen, after going through a successful phase equilibrium simulation. And of course, you also, for this, you need some input. You need the initial concentrations of the trace elements, isotopic compositions in the magma, in the wall rock, and in the recharge magmas. And of course, what is important are the solid melt And also, if there's a fluid phase, and if you think fluid phase is important, also solid fluid partition coefficients, which may sometimes be important for elements that are compatible to fluid phases. It may completely change what is going on in the magma. It's possible to input constant or temperature dependent partition coefficients. So you can also do the modeling so that the partition coefficient changes when the temperature drops. So that's what you do with the traces. And we wanted to make this useful so that every time you run it, you don't have to manually input the partition coefficients every time. It would get tiring pretty soon. So it is possible to make these kind of predefined partition coefficient sets, which are called PAR files, where you can store this information. Also, you can store the compositions there, the initial compositions and also the isotopic compositions. Maybe I will quickly show you one of the PAR files. So this is how a PAR file looks like. There's first info when it was created. This was created 2 years ago, this PAR file that we are using. You can list isotopic compositions here for the magma, for the different elements. For lead, you have 3 different isotopes. These isotopes you can input them for the wall rock, for the recharges. So of course you can input up to 30 recharge values here. Also element concentrations. Now this is just you can see there's hydrogen and helium. So our programmer kind of like didn't want to just select which elements to put here. So we just put all the elements here, unfortunately, probably for some users. So you just have to find which element you are modeling and then input the concentration for it for the magma and for the wall rock and for the recharge event. So you can store the concentrations here. Of course, you don't have to input them manually in Excel. You can input them in the trace element modeling tool and then store the file there, which may be more useful. And then, of course, the partition coefficients for all the phases. And there are about 60 phases that may be stable in melts. So you probably guess that this is quite a list of partition coefficients that you can use. And of course, also taking account partition coefficients to the fluid phase. So you can input about 40,000 partition coefficients here. Of course, you don't need to input all of them. You only need to input the elements that you want to model and for those phases that are stable in your modeled system. Okay. I think we have to move on in this point. Always takes a little bit more time than you think. I will now switch back to my modeling Mac because it's now ready. So here we go. So this is now the final message from the primary MCS that everything is ready. You probably have the same message if you were running this on your own. Just click OK. And then you can export the run results. So now the file that we just went through quite quickly is created. The primary MCS output file. So now we are ready with the phase equilibria and major element modeling. We can close MCS. Never save on MCS. Always click don't save when you are closing it. Now you can also close your terminal and command prompt windows. You don't need melts anymore for the trace element functions. It has done its job. So now in the same MCS VPL code folder, you just click the MCS trace element isotopes application. Again, I have many of these here because I have tested different versions, but just the one that you have, just click that open. Enable macros. Okay. And again, you have to choose the MCS folder here. Okay, I will zoom in a little bit so you see the menus. So this is also quite straightforward. The trace element tool. We start from the top button and move downwards in the scheme. In the beginning, when you have not yet uploaded any MCS output, it shows you every different possible input that there's possible to, or every possible button that you can have on this interface. So up to 30 recharge events. But we don't need that many, we only have 2. So let's select the file that we produced. I named it AAAAA test. You may have named it differently. And just finish. And now you can see that when it uploaded the MCS output, it automatically enabled the buttons that are relevant to this specific run. So there's fluid in the Magma, there's fluid in the Warrock. It asks for the fluid partition coefficients because of that. And there are 2 recharge events for which you need the element and isotopic input. Of course, partition coefficients are not required for the recharge Magmas because they come in and are completely homogenized in one step. So that's the reason why partition coefficients are not input for the recharge Magmas. Then, of course, you want to select some trace elements. Again, something that you can do here to fool MCS, what we have actually done, is that if there's an element that you would like to model, but it's not available, it doesn't really make any difference which element you choose. This is just a computational limit of how many elements we may have available. And that's why we have defined the elements that we have here. But for example, when we modeled sulfur as a trace element to test these kind of end member scenarios, we used, I think, scandium as sulfur. And basically nothing, the computations are not different. Anything between which element you are modeling doesn't make any difference. Of course, you have to keep track of yourself of what element you are modeling. And of course, it's easiest if it's already predefined here. So then you don't have to remember that, okay, I actually modeled like, I don't know, like bismuth as palladium or something like that. So let's select a few of these. And I think for the default run that we have oxygen there. Of course, it's not a trace element, but you select it nevertheless in this same menu. Nickel, zirconium, barium, and I think there was lanthanum, neodymium, and strontium as well. Maybe we'll cope with these. Maybe there was ytterbium as well. Let's see if we can select that one as well. You can select all as well if you like. And you can also load the previous selection. So again, you don't have to always select the elements again, but MCS remembers which elements you selected the last time. Okay, set initial concentrations in the Magma. Again, I think I have to zoom in here so you see something. So here are the elements that we selected. You give the initial concentration for them. For oxygen, you don't obviously give any concentration because that is stored in the MCS output. It calculates the oxygen concentration based on that. You just give the isotopic ratio for the Magma. For strontium and neodymium, we selected them, and for them, isotopic modeling is also possible. So you can also put isotopic composition here. So these are, I guess these are in ppm for all the trace elements. Then the partition coefficients for all the different phases. If you see only one value in the cell, like for example, nickel in olivine, it's not then temperature dependent. So if there's only one value, it's the same value throughout the run. So these cells then that give these more complex numbers, let's see which could be a good one to show, maybe one of these last ones, or spinel. So here it says 0.006 at 1130 degrees Celsius is the partition coefficient of nickel in spinel. And at 740 degrees Celsius, it's 0.2935. So partition coefficient temperature slash partition coefficient slash temperature. And this is how it calculates the logarithmic correlation between these two values in order to make the partition coefficient to be temperature dependent. So all of those values that have those slashes, they change according to temperature. Okay. And of course, you put this for fluid. If you are not interested in fluid, or if fluid is only a minor small bubble in your run, you may put all of those as one. Then it kind of like takes the fluid out from the trace element calculation. So don't be troubled if you don't find or don't want to have to find values for partition coefficient for let's say like clinopyroxene. How is nickel partitioned in clinopyroxene and fluid? Well, I guess there is even no value for that available in many cases. Here they are input as 1000, which means that nothing basically goes into the fluid, so everything stays in the melt phase. But for some elements that are compatible to the fluid phase, this may be important. Same for wall rock, I won't go through there. For recharge, you only input the initial concentration, so no partition coefficient for recharge. Again, once you define partition coefficients, you have found partition coefficients that you like to use, you can save them. And unfortunately, I can't zoom into this one, but you can select which things to save, which things to load. And we are now loading a PAR file that was used together with this default run, and which I just opened for you. So let's see, I think it was this one. Yeah. That one with a very long name. I think you shouldn't have too many of these. PAR MCS default and so forth. So now it opens the PAR file and it fills all the cells with the values that have been predefined and stored. Seems to be taking some time now. It's probably because the zoom is taking place at the same time, so it's a little bit slowing this down. I think we are soon there. Yes, there we go. Okay. And now I guess all of these values have been predefined. For example, you see that nickel in olivine is now 10, so it was another value that we used in that input. Okay, then what you do is that you just perform MCS trace element isotope computation. That will take about 5 minutes. So I think I won't do it here now. You can click this on your computer and continue following the presentation. I think we need to save some time here. But anyway, that's then everything that we have to do. Then we are ready with the output. So we can stop sharing here. So after you have done that, the MCS traces isotopes application have written three new tabs into the same output file that we looked after the phase equilibrium arrives. And there's Magma. Magma output, so compositions of trace elements in the Magma and its phases. Again, you can see that in the beginning, it shows all the input that you use. So you never lose the input that you used for any run. You are always, input is always stored, so you never lose that information. Then some selected parameters from the MCS output, so you can follow the basic run. And then the concentrations of the elements and isotopic compositions in the melt, in the Magma. Then the trace element concentrations of each phase in instantaneous phase, so phase that crystallizes at that step. And then I guess in bulk cumulate, so you can also calculate, or it calculates the amount of trace element in the bulk cumulate. Also in fluids, the amount of trace element in fluids, of course, here it is 0 because they were incompatible, completely incompatible to fluid. Partition coefficient was so large. You can follow the evolution of the partition coefficient, the bulk partition coefficient every step. And in the end, we have the oxygen isotopic composition. Alpha values are not input for oxygen. So we thought that the fraction effect of fractional crystallization is usually so small, and there's so little knowledge on the alpha values that they are not taken account. So you can see oxygen starting to change only when assimilation begins. So a lot of information stored in the output file. Just highlighting few things from the trace elements. Here you can follow these different events. For example, this is Magma melt strontium composition versus the isotopic composition. Of course, no change in isotopic composition until assimilation begins. And you can see as first strontium being enriched in the melt until plagioclase crystallizes. Assimilation begins, strontium isotopic composition starts changing. First recharge event again takes us back towards the melt. Plagioclase is not crystallizing, we are not losing a lot of strontium, but assimilation is taking place, strontium isotopic composition getting enriched. You can follow these different events taking place in the system. And you can even theoretically like follow like zoning in a crystal. If you would think that there's a crystal that kind of like fractionates away from the system, but still records the processes in the magma chamber in the outer rim, we could see isotopic zoning in plagioclase, for example, recorded here. So in different simulation steps, depending whether there's assimilation taking place, whether there's recharge that has taken place, different zones of strontium isotopic composition in that phase. And of course, there were breaks in plagioclase crystallization as well. Just kind of like an extreme example, what you can dig out of this amount of data. Okay, here are some relevant publications that I've already distributed to you. Some examples of applications to natural systems. And one that we are going to briefly talk about here is the one where we actually tried to model sulfide saturation, although sulfur is not part of the melts algorithms. But we will show you an example how we did it, and maybe you can try it yourself like that. So that's end of phase 2. How are we doing there? Were people able to run?
Yeah, if you're able to run it, just let us know in the comments there. If you have any questions, raise your hands or just drop a question and I can relay them. The Monte Carlo idea of putting in several parameters is quite powerful. I think that would be amazing, wouldn't it?
Nice, Wilson, you got it working great. Yeah. I mean, that would be a game changer, because I think most of my time in these studies have been spent on mining the output and trying to do another run, changing the parameters, and you have to do it manually. And of course, it's easier when you have the separate computer here, so you can run it and then do something else. And when it's finished, then you check it and make another run. But I mean, thinking that you can have 100 runs overnight and then just check them in the morning would be amazing.
That'd be amazing. Yeah. So Sarah's raised her hand, so I'll just mute and give way to Sarah.
And Coint, nice working as well. Yeah, cool. Okay, Sarah, please.
Sorry, I'm sure we don't have to bore everyone else with my stupidity. So I got lost because I couldn't get the terminal thing working in the beginning because the window you showed was not for Windows 10. So anyway, I finally got the terminal running, but then I couldn't get anything else to run because, of course, I'd lost my way. In the terminal, when you've got the terminal running, do you have to give it a specific directory or anything?
No. When the command prompt starts, you should be able to just paste the commands from MCS to those.
Well, I'm missing an essential step, pasting the commands clearly, because when I try to run it, of course, it doesn't do anything because I haven't pasted the command. So,
would you be able to share your screen, Sarah, and perhaps just so you could see what's happening? Is that possible? I mean, I could make you a co-host if you think that would be helpful.
Yeah, I just don't want to bore everyone else with my stupidity.
Oh, I'm sure other people might have had similar issues, maybe.
Okay.
So maybe I don't know. Maybe better would be that I share the screen and show how it's done here.
Okay, sure. If that's how I think, let's do that.
Is that okay, Sarah?
Yes, I will. Okay, I've got as far as getting the prompts up. I've got a screen which says C user SJ Barnes with 3 prompt commands. I remember that.
Yes, that should be okay. So I will once more. Maybe this is useful for others as well. I will just.
I hope so.
We have a little bit of time, so I can show this once more. So let me share my I'm sorry, I have to share my Mac, but it's the same thing there. So I will just show you it once more. I'll do this.
And I've got to put that on full screen.
Okay, so now when you have the terminal windows open or command prompt, this is my command prompt on Mac. So
just a minute, I closed my MS. Okay, yeah, just a second. I closed the simulator just to be sure I was in the right place. Okay, so I've got the simulator open. Should I close all the terminal screens first, or should I just leave the terminal screens there?
If you haven't done anything with the terminal windows, you can leave them open, but otherwise you can reopen them.
No, I don't want to go through that again. I'll just leave them open. Thank you.
Okay. So the next step that you would have to do, I think this is the kind of like the trickiest one. So after that, you just click the commands in the MCS, like the step 2, step 3, step 4. But this first one is only where you have to work with the command prompts. So it's Melts terminal commands.
Yes.
You click that one, and then there are the 3 different.
Yes, I selected Rhyolite Melts. Yes.
Yeah, and Rhyolite Melts 1.2.0.
Yeah, no problem.
And then
you put on clipboard, right? You
yes,
have to click. So then the number sign appears.
So then you should be able to paste it here in the one of the command prompts.
Okay, let me look.
You can right click on the window and then select paste.
Okay, so I should do. I should copy the bit that says C uses SJ Barnes documents, blah blah blah.
Yeah, just put it whatever when your command prompt opens. Just put it in that like root, whatever it's written there.
Okay, Control
C. It should work like that.
Okay, command prompt. I do that 3 times?
Yes, for the you do it for 3 different command prompts. So you would have to have 3 different windows.
Yeah, and okay, so,
and of course copy the different commands. So like the Magma and the Wallrock and the recharge command.
Okay, okay. So I would do that.
Yeah, I think we can probably move forward and you can try this and we can return to that after if it still doesn't work. Okay.
Yeah. Okay. Yes.
Thanks.
Thank you. I will try that and come back to you.
Yes. So it seems a couple of people have had it working well, so hopefully you can get Sarah up and running there as well.
Yes, that's very nice. I'm very happy that people were able to do it. Because it's always, I've been using it so much, so I always, I'm troubled if I'm going too fast. But
it's always the little things that screw you up.
Yeah, it is easy to get lost. I completely understand.
I think I had an issue and I started using it because I had a Windows Explorer file open and it didn't like that. But once I closed everything down and it was just the command prompt and the Excel file, it worked.
Yeah.
So
and
some just little,
It doesn't like other. It's jealous of your attention. You could say so.
Yeah, if there are any questions, I mean, I did jot down a couple actually as you were going there, Yossi. Because it equilibrates the wall rock, and then as it reaches a certain, thermal equilibration, the assimilation process begins. Is there a way to produce a sort of a time series, just thermal diffusivity output between the magma and the wall rock?
No, so there is no time dimension in MCS. So it's basically just a thermodynamic equilibrium model.
Mm.
So it's kind of like, of course, you think when your temperature drops that, okay, some amount of time like passed when that happened and when there was assimilation taking place or crystallization happening, but in reality, like there is no time dimension in the system. So I don't know, I don't know how that could be done currently without inputting like huge amount of this kind of kinetic code into the.
Yeah, I think that'll be really interesting. So
yeah, for sure.
And another thing I thought of is I spent some time trying to model trapped liquid shift of cumulus minerals. I wonder if that's something. There's a workaround in MCS that you can model something similar like that.
One of the postdocs that was in the project, Kieran Isles, did this to some degree, at least in his work on Lachlan fault belt granites. So it should be out in Journal of Petrology. So what he did is that there's a cumulate calculator tool for MCS, which you can also download from the website, that calculates the major element bulk cumulate compositions and wall rock residual compositions for every step, because that is too much stuff to have in the MCS output.
Yeah, sure.
So for people who want to look at the cumulate compositions, we have a separate tool, so you can download that from there, and with that you can do this kind of mixing calculations with the cumulate part and the melt part. So I think you should check what Kieran has done and maybe ask him about that.
No, that's great. No, thank you for that. Okay, there's a question in the chat from Jonathan. I'll read it out. Does MCS take into consideration crystal lockdown temperatures and may not allow to recharge if a magma has crystallized, for example, more than 50%? So
that's a great question as well. MCS forces the recharge, so no matter how much it defines it in the input file that this is when the recharge comes in. But you can follow this, of course, from your output run that, okay, when the recharge comes in, there's only 20% of melt present. So then you would say that, okay, well, this is probably not possible. What you would do then is to, raise the temperature of the recharge magma when it comes, or raise the trigger temperature for the recharge magma when it comes in. But then it would come earlier and you would see what happens. So a lot of this MCS use is so that you test different scenarios, and depending on what you are interested in studying, you just try to find the parameters that are the most crucial for your system to work. So basically the recharge would happen, but you would see from the output that it happened at this point, which doesn't make much sense. So although there are thermodynamic limits, there aren't really like kinetic limits in MCS. So this is something you have to kind of like use your own brain to go around with these kind of issues. But very good question.
So, and a second question, more with setting up the simulations. I've had a problem that my command prompt seems to have misread the wall rock composition as it gives me errors on step 3 of the input file.
That doesn't sound like I would have a solution for that right away.
Okay. Perhaps if Maximilian could just give maybe a bit more detail on exactly what happened there, and we can perhaps just he can guide you a little bit easier there. I'd appreciate that, Maximilian. Thank you.
One thing is that you would, I don't know if it's already something that it reads in the previous steps, is that you would have to have decimal defined as point and not comma. I don't know if that would be related to that. But
does it have any issues if you have, say, if you accidentally put a trace element for a wall rock that you didn't define in the Magma? Because I know the melts read files need the assimilant and the wall rock to look identical. So, for example, say you accidentally put in nickel oxide in the wall rock composition, but not in the Magma, would it still continue to go? Or
yes, it will. Then it will be so that
just be from 0.
Yeah. So in that, if let's say you have an element oxide in wall rock, but not in Magma, the wall rock is treated by the separate melts engine, so it calculates equilibria for that. And in the first partial melt batch that comes in the Magma and contaminates it, there probably will be some of that element, and then the Magma will have it as well. But as long as those systems are isolated before assimilation takes place, the other oxide doesn't exist in the Magma.
That's interesting.
Okay, I think that I think the issue with Maximilian is probably that this is the error message that you have. So you would have to define decimal as point and not comma in your whole system, and in Excel as well separately. And I'm from Finland, and in Finland our decimal point is comma, and I always have to change it in every computer that I use, that I'm able to use any kind of petrological or geochemical plotting software, because it always creates this problem. So you would have to define that I think in both in Excel and also in your computer settings. So you should try that. And that's I'm happy that I was able to trace that problem with that. Yeah.
Okay.
Good.
Yeah.
I think I will answer the question of Jonathan still, but then I think I will shortly go through the final session. It's actually not very long, so just to give you an application that you may be interested in. But okay, how to properly enter wall composition of very heterogeneous sedimentary sequences. That includes significant sulfate and coal beds, for example. Yeah, that's it. Well, it is problematic, but you could try what I would do in that case, I would give some kind of average composition. I would give some kind of end member composition from the other end and end member from other end, and then first test with that kind of compositions, and then see what the output is, and maybe try other combinations. But for example, if there are coal beds, again, I don't know how well the melts can kind of like generate phase equilibria of that kind of wall rocks when they are not like homogeneous. But it's certainly something worth testing. So I would start with average and some end member compositions and see whether melts is even able to handle them. So you always have to make some kind of compromises in these things. And sometimes it may be that MCS just doesn't work for the compositions that you want to model. And then you just have to try something else. Okay.
Okay, great. I think we'll pause the questions there. But if anyone else has any success stories from running it, please drop them in the comment box there. And I'll let Jussi carry on with the final session.
Yes. So a lot of this that I'm showing now is actually something that has been already presented in a couple of meetings. You probably have seen these presentations or read the publication that came out in Economic Geology just in the beginning of this year. A lot of this work is Ville Virtanen's work, the PhD student who worked in my project, who is very close to graduating now. And if you have any detailed questions about this one, I think you should email him instead of me, because he is the primary motor in this study. So here we show an example how we modeled sulfur using MCS, although sulfur is not part of the MELTS algorithms. How does and this is one of the most interesting results here from this study is that how assimilation affects sulfide saturation, not regarding whether there's sulfur coming from the wall rock or not, because this is the first time I think that we are looking at the whole range of different elements, the effects of mass exchange and effects of heat exchange on this matter. So very interesting results came out from this. I think I will skip most of the introductory parts here. In order to save time, you all know what SCSS is, sulfur content at sulfide saturation, and it depends heavily on melt composition, also, of course, on temperature and pressure. And sulfide saturation occurs when sulfur contents exceed SCSS. And usually it is thought that assimilation of sulfur-bearing wall rocks is one of the most effective processes in forming these, some of the large sulfide deposits. So we wanted to study this using MCS and thermodynamic approach. So like said many times already, the traditional binary mixing or AFC of De Paulo, they lack thermodynamic constraints. So usually in many models using SCSS, it's just like some things are introduced in the magma, like saying that, okay, SCO2 in the magma increases, or sulfur increases, or H2O increases, but we are trying to look at the whole big picture. So the heat budget, the phase equilibria, and it's also very easy to forget when you are doing this kind of modeling, that there's also mass that is being introduced in the magma. So let's say assimilation is taking place, but you don't have sulfur in the wall rock. The mass of the magma chamber increases, which means that the sulfur concentration in the magma is diluted because more mass is being put in the magma. So it doesn't stay the same. It is being diluted if there's no sulfur in the wall rock. So some of these basic things are very easy to forget without actually doing the modeling. Yeah, just a nice example from Duluth complex magmatic rock recrystallized partial melt in the contact sedimentary xenolith. So we know that these assimilation processes are actually taking place. And just a closer image of what is happening there. So partial melting is traditionally neglected in geochemical models. Not in all, some people do that model partial melt assimilation as well, but not nearly always. And MCS was used, rhyolite melts, engine version 1.2.0. And the whole system was being kept book of. And Duluth complex was the system. Virginia formation black shale thought to be a major source of sulfur here on its western contact. Huge intrusive system. A lot of nickel copper PGE deposits in the contact zones of the intrusion. So we selected parental melts according to the cogenetic mid-continent rift basalts, and actually found, and this is something that people have also done previously when modeling Duluth complex, using the basalts as parental melts. And we pre-tested different H2O contents, different oxygen fugacities for the magmas in order to find out how the phase equilibria changes when we change those parameters. Very common way of working with MCS is that you try a little bit changing the parameters, see if there are any major changes. If there are not, then those parameters are probably not that important and you can move forward. And we found like the best ideal water concentration and oxygen fugacity in producing the rocks that we actually see in Duluth complex. So that's how we defined the parental melt composition. Black shale wall rock, pressure 2 kilobars based on mineral assemblages in the contact aureole, and sulfur modeled as trace element here. Of course, in nature, there's phase equilibria of sulfides in what is important. But since we don't have at least MCS compatible tool to study it, we kind of like just try different end member scenarios for sulfur to be either compatible or incompatible in the wall rock. So here's an example from a drill core from the Duluth complex, and there's a certain section, sulfide per section here, which is thought to crystallize by fractional crystallization. We kind of like try to replicate this with MCS without doing any assimilation yet, just trying to replicate if you can replicate fractional crystallization scenario in Duluth. And this is the best that we got. We got some troctolite, we got some augite there as well, but not exactly producing the same scenario that we have here, but the rock types are very close to each other in this classification scenario. You remember, these are, of course, man-made classifications, and the compositions major element-wise may be quite close to each other. So this is this kind of model with just fractional crystallization. And when we did assimilation modeling, both using the partial melt assimilation and then the stoping bulk assimilation, where we just put xenoliths in the wall rock and just homogenize them with the magma, we got norites and gabbronorites, which are found here in seals and in contact zones with the black shale rock, which kind of like again suggested that there's something that these assimilation models are showing that is actually observed in nature. So for the SCSS model, we used this model of Smythe et al. Using average sulfide composition of the copper nickel deposits. That was the only thing that we were able to, or that is what we use as a standard default model. Initial sulfur content in the parental magma was 800 ppm. And just using fractional crystallization, you see the SCSS trend here and S in melt. Just if you do just the fractional crystallization model, at 12 weight % of crystallization, sulfur gets saturated in a fractional crystallization model. In AFC, the SCSS trend drops quite considerably, at least in early phases of the model, when there's not much cumulus that have formed. And it's funny or very interesting that with MCS we can actually isolate these different effects that it has on the SCSS. So assimilation increases silicon, aluminum, potassium, and water in the magma, which lower SCSS. And also FeO, NGO, calcium, and sodium are depleted in the melt, which also lowers the SCSS. So many of these different effects of assimilation actually lower SCSS in AFC compared to FC. So if the wall rock is sulfide poor, now we are in the first partial melt assimilation scenario. This is the sulfur concentration in the melt in AFC scenario. The sulfur content of the melt actually increases slower in the AFC model than in the FC fractional crystallization model. And this is exactly what I highlighted previously, is that because we are adding a wall rock that doesn't have any sulfur, sulfur actually gets diluted in the melt. So, of course, black schist in Virginia formation is sulfurous, but we wanted to test these different end members. So only assimilation of, let's say, granitic wall rock with not much sulfur, although SCSS values, SCSS may be lowered by these effects that we also see here. The sulfur concentration in the magma may get lower because of that, and then we necessarily don't see major effect because of that. Very nice outcome from these models. If sulfur is compatible to Virginia formation wall rock, meaning that we use partition coefficient of 100, it's almost the same than in the fractional crystallization case. So if there's some phase keeping sulfur in the wall rock, then it doesn't really although SCSS is surpassed, there's not much sulfides that form. If it's equally compatible to wall rock and wall rock melt, then you see already quite a drastic effect in sulfur concentration in the melt, a lot of sulfides produced. And if it's very highly incompatible, partition coefficient of sulfur 0.001 in wall rock, a lot of the sulfur comes straight into the magma, and there's high amount of deposition of them. This end member could also kind of like approximate early fluid assimilation from heated black shale. And these two scenarios, either with partition coefficient of 1 or smaller than that, are compatible with sulfur isotopic data for the Duluth complex, which is probably not surprising. The stoping models where we have bulk assimilation of wall rock, they are very similar to the trend with AFC, the assimilation of partial melts with partition coefficient of 1, which kind of like makes sense. But anyway, this is also possible, kind of like this bulk destruction and just mixing with these disintegrated xenoliths. So the main result from the study is compiled in this figure, and what is important that although in these we see in all of these models that the sulfide saturation is always happens quite early in the system, regardless whether there's fractional crystallization, regardless whether that's an AFC model, the sulfide saturation always happens very early. But the amount of sulfur that's deposited and the amount of stratigraphic thickness that it's deposited within changes drastically within these models. So in fractional crystallization, without any assimilation, the sulfide content of this cumulate pile that crystallizes in magma chamber simulator is actually quite small. It's kind of like this disseminated sulfide all around it. Even if there's assimilation taking place without sulfur in the wall rock, or if sulfur is compatible to the wall rock, it's kind of like looks the same. So not only this disseminated sulfide with not much mass of sulfide present. But especially if sulfide is highly incompatible, even enriched by fluids or very early melts in the system, that's the way that we get these high amounts of sulfide deposits in these quite thin layers of these intrusions. So that's, we think that that's the way to go. So there's either fluids or very early partial melt assimilation, or both taking place. Of course, dynamic sulfide accumulation is not considered here, which may be an additional factor which shouldn't be overlooked. And of course, we want to express that this is not a perfect model because kinetics are not taken account. But anyway, it's just something to, so kind of like the first test on how this tool worked on this kind of sulfide systems. So I guess that's it. Conclusions: assimilation effectively lowers SCSS. Selective assimilation more efficient compared to bulk assimilation. And sulfur-bearing wall rock is required to significantly promote sulfide saturation. It's kind of like makes sense, but these are kind of like robust tests for those claims. Okay, there are of course multiple ways to go forward from here. Probably something that I want to show in the end of this is how Ville did this. So Ville shared his sheets where he did this, and I'm not an expert on them, but I will just quickly show what he did so you get an idea about that. Of course, I haven't opened them, so let's see. Okay, you see my old friend is taking a little bit time opening it now. Shouldn't take this long.
That's okay. I guess while we're waiting, I'll just say if any more questions, continue to drop them into the box, and
sure.
We could do that as well after this.
So yeah. So as this is Ville's sheet, how he did these calculations. It hasn't been cleaned, it hasn't been streamlined. There will be probably ways to do it more efficiently, but he has selected or copied and pasted some of the output from the MCS, basically masses and then melt compositions. And then he uses these different, he calculates these different parameters, like these, let's say, like the silicate mole fraction oxides from the major element data of the melt composition, and then uses these different models like Smith et al., Lee et Ripley, and so forth, Fortin et al., to calculate the SCSS based on those melt composition parameters. And I think there may be masses involved. Oh, temperature and pressure is of course involved in them as well. So he gets these different SCSS values, and then those values are used on these trace element assimilation outputs from the trace element model, where sulfur was considered as trace element in the system, and that way we get how much sulfide is crystallized at different points. So this is the model for when the partition coefficient is 0.001. This is for partition coefficient of 1 and so forth. So that's how these different trends were created. I'm sorry, I can't go into more detail in that because a lot of that happened in Ville's sheet and in his head. But if you want to know in detail how to do this and maybe try to develop it further into the system you are modeling, just contact Ville. And his email address was there. And of course, you can reach him via me as well. Yeah, I guess that's all.
Great, thank you for that. I'll just take a moment to thank Jussi for sharing some of his wisdom using the Magma chamber simulator. It really is a great bit of kit, and it seems the limitation is really your own creativity in some instances. So that's awesome. So if there are any questions, I guess we can hang around until on the hour, if that's okay with Jussi, and any more questions, or if anyone else has any issues from running the program, perhaps we can try and solve that in the next 10 minutes. I guess one sort of final question for me that isn't really technical, it's more sort of based on presentation and how we might use these, is if you're going to read a publication that uses Magma chamber simulator to model crystallization or assimilation, what kind of plots, outputs, data would you expect to see, or should you see, either in the actual document itself or in supplementary materials? What's best practice essentially in using these?
Yeah, that's also a very good question. I had some. I had to go through those same questions when I've been publishing these studies. So what I usually do is that for electronic appendices, I put all the modeling output files there. So that way they are always available to everyone. Everyone has seen what I've done, and I think that's quite useful. That may be sometimes quite a massive file, but I mean electronic appendices can be quite big nowadays. And of course, in all of those output files, MCS has stored the input as well, so everybody can run them again or change the parameters if they like. That's one thing I like to do. Also, in describing the model itself, I usually go, of course, depending on the publication, how much there's words that you can write. I usually refer to these MCS studies that I've distributed to you, and then just mention that everything else was default, and as explained here, this is how it works. It's explained in these publications, but in my model, I change these parameters. I use this parental melt composition. I use this Walrock percolation threshold value if it's not default, and so forth. That is usually how I go through with it. And then depending on how you want to show it, we discussed already during this workshop that it's maybe sometimes useful, or maybe quite often useful, to show the visualizer output or some kind of like section that this is actually what happened, showing that this is what crystallized, this much melt was left in a single diagram, or then list the output in some kind of table. But this depends a lot on what you are studying and how important part of your study MCS is, I think. Does that answer, or is there something?
Perfect. No, thank you for that.
Yeah,
I think that's important. Okay, so again, we'll hang around for 5 more minutes. So again, any questions, but participants are free to leave. I thank you for attending and sharing this workshop with us. So I really appreciate that. And hopefully I see you all at another workshop or at the symposium itself in the coming weeks. So thank you, everybody.
Yeah. Thank you all. It was very nice that I'm very happy that you were able to run the runs that you did.